Now let's consider another example where I would like to find the load impedance, and I know, perhaps I can measure the input impedance and the length of the line. I also have a characteristic impedance Z0. Let's say that I measure that Zin is 100 minus J 100 ohms. My line is 50 ohms, so my Zin, when I normalize it, is 2 minus J2. Let's plot it. Real part of 2, imaginary part is negative, it's below the central axis. Right there is my point Zn. Now since we're going to be going a distance L, rotation, I'm going to do the same thing I did before and draw a straight line from the center through my point out to my outer axis. But this time, instead of going towards the generator, I'm going to be going towards the load. Right here, see, that's towards the load. So I need to use a different axis. Right here, we've marked wavelengths towards the load, and it goes in this direction. So this axis is the one that I'm going to be measuring for this example. Now let's say that my line is again 0.2 wavelengths long. Let's read off our value right here. Looks like that's about 0.21 wavelengths, and I am going to move towards the load a distance of 0.2 wavelengths. So I'm going to go out here to 0.3, 0.4, 0.37, 0.39, 0.41. So the distance that I'm going to go is 0.21 plus 0.2 wavelengths. I'm going to go to 0.41 wavelengths, which is right here. Then I'm going to again draw my straight line from the 0.41 to the center of the Smith chart, and I'm going to mark this distance on my piece of paper and move it up here, where I'll go from the center to this point right there. So this 0.2 wavelengths towards the load takes me from my input to my load impedance. Let's read my load impedance. It has a real part right here of 0.35. It has an imaginary part of about 0.55. Again, we're not in ohms, so to get it to ohms, I need to multiply by Z0, and that will tell me my load impedance in ohms. So realize what we have done here is we have moved back and forth towards the load if we know the input impedance, and towards the generator if we know the load impedance. Now I'd like to talk about a few other complexities on finding this distance. Let's consider what would happen if my length had been 2.2 wavelengths instead of just 0.2 wavelengths. Well, what I would have done is I would have started here and I would have moved towards the load a distance of half a wavelength, which would have brought me back to exactly the same point I am here. One time around the Smith chart is equal to 1/2 of a wavelength. So I would have gone half, around again would have been 1, around again would have been 1.5, yet again would have been 2, and then I would have gone my 0.2 wavelengths and ended up at exactly the same place. So in order to find the length here, I'm going to subtract off whatever even number of half wavelengths I have, and I'm going to plot 0.2 wavelengths just as I did before. Let's look at one other problem. What if I had ended up with a length such as 0.4 wavelengths where I had to go past this center point of the Smith chart? So what if instead of going to 0.41, I needed to go to 0.61? Well, there isn't a 0.61 here. Look how this goes. 0.21, 0.25, 0.32, 0.41. When I get right to here, it's 0.5. So I can keep counting. Right here, so this would be 0.5, about 0.51, 2, 3, 4. This point right there is 0.54, 0.55, 0.56, 0.57, 0.58, 0.59, 0.6.